The Electronic Display System, EDS, presents primary flight, navigation, and system information to the flight crew. The EDS consists of 5 display units, a guidance panel, 2 cursor control devices, CCDs, 2 multifunction control display units, MCDU, the ICOS full button, 2 reversionary panels, MAU hardware including control input-output modules, and an EDS application software on dedicated processor modules. The 5 display units are located on the main instrument panel. There are 2 primary flight displays, PFDs, 2 multifunction displays, MFDs, and an engine instrument and crew alerting system, ICOS, display. The display units are identical. In case of failure of one display, an automatic logic transfer will allow its information to be presented in the remaining units. All of the components require 28-volt DC power. The pilot's PFD, the co-pilot's MFD, the co-pilot's CCD, the pilot MCDU, and co-pilot's display controller are powered by DC bus 1. The co-pilot's PFD is powered by DC bus 2. The pilot's MFD and CCD and the co-pilot's MCDU are powered by the DC essential bus 2. The ICOS is powered by the DC essential bus 1. The pilot's display controller is powered by DC essential bus 2 via SPDA 2. The electronic display system abnormal operation is the automatic and forced display units reversion. The 5 display units are numbered 1 to 5 from left to right. Only DU2 and DU4 can be reverted. DU1 and DU5 are always operated as PFDs, and DU3 is always an ICOS. Each pilot can manually select the desired display on the MFD screen via the display reversionary panel. The 4 switch positions are PFD, Auto, MFD, and ICOS. Setting the switch to a position other than Auto forces that selection onto the MFD. In this case, the failed reverted from display unit is shut down, and the display will be blank. When the switch is set to the Auto position, the system is in automatic reversion, with manual override capability, and it will detect many types of display unit failures. The reversion system will reconfigure the remaining DUs to the configuration shown. The guidance panel houses 2 display controllers and a flight guidance panel. The display controller has the following controls. The combined baro set, standard, units knob has 3 functions. Turning the baro knob sets barometric altimeter correction. Pushing the Push STD button sets baro correction to standard, and selecting the IN HPA switch selects baro correction format to inches of mercury or to hectopascals. The combined RA baro minimum mode knob has 2 functions. The outer knob selects the source, either barometric or from the radar altimeter system, and the inner knob, when turned clockwise, increases the decision height. The HSI button toggles between full HSI and partial compass arc displays. The WX button selects weather data for display. The FMS button selects FMS as the primary navigation source and toggles between FMS sources. The BRG buttons toggles between VOR, ADF, and FMS bearing sources. The upper button, Circle, is for System 1, and the lower button, Diamond, is for System 2. The Preview button selects Navigation Preview. When FMS is the selected navigation source, it is used to display VOR, localizer lateral and vertical deviation, and distance on the HSI. The VL button toggles between available short-range navigation sources. The FPR button turns the flight path reference line on the ADI on and off. The primary flight display, PFD, is the flight crew's primary instrument. It provides display of aviation and navigation information as well as backup radio tuning. The PFD is divided into sections, each one presenting one group of information such as information regarding airspeed, altitude and vertical speed, attitude, heading, flight modes, and tuning COMMS and NAV. On the guidance panel, the display controller portion allows the selection of primary flight display HSI formats, navigation sources, weather display, and bearing pointer selection. Certain PFD internal failures will result in a blank PFD screen. In case of mismatched information between the two PFDs, a flag will be shown in the dedicated indicator. For example, a CAS flag is displayed whenever airspeed miscompare is detected, or a log flag whenever a localizer miscompare is detected. Here you see an overview of all flags which could appear in case of a PFD miscompare. In the event of a display failure, information may be presented in the MFD by appropriately setting the reversionary panel. The multifunction display presents navigation information, shows aircraft's system parameters and status, and enables maintenance personnel to access maintenance messages. The MFD display consists of control and information areas. The menu soft keys, on the top and bottom of the screen, are used to select formats and control various systems. The selected information is displayed on the split-up screen. The cursor control device, CCD, in the center pedestal is used to control the menu soft keys. Once a soft key is pushed, a pull-down menu is opened. Checkboxes in the menu are used to select and deselect each function. For navigation, you can choose between the map and plan formats. Weather radar, FMS, TCAS, and various other information can be shown or alternatively switched on and off. The Systems menu has 7 synoptic display subpages available for monitoring the respective aircraft system and for fault isolation. These are the pages for status, flight controls, hydraulics, fuel, electrical, environmental control system, ECS, and anti-ice. In addition, the following pages are available for maintenance: the engine maintenance page, the maintenance page, and the system configuration page. Pushing the TCAS soft key opens the TCAS controller. Actuating the weather button pops up the weather radar virtual controller. Via the checklist soft key, you access the electronic checklist, which allows selecting among normal, abnormal, or emergency procedures indexes. The Engine Indicating and Crew Alerting System display, ICAS, presents engine indications, system parameters, and crew alerting system, CAS, messages. The engine instrument display consists of IN1 display, ITT display, IN2 display, and fuel flow display. Separated but appendant to engine indicating, there is the fuel quantity display, the oil display, and the engine vibration display. There is the slat, flap, speed brake display, the trim display, the cabin display, the auxiliary power unit APU display, and the landing gear display. The crew alerting system message window provides the pilots with displayed alerts. Remark: in case of failure in the ICAS display, its information may be presented in the MFD by appropriately setting the reversionary panel.
Welcome to the course on Head-Up Guidance System. By the end of this lesson, you should be able to identify the components of HGS and its interface, identify and explain the indications and enunciations associated with HGS, and explain the operations of HGS main components. The HGS is an electronic display system that generates and projects information in the pilot's forward field of view. The system displays flight and navigational data in a semi-transparent crystal screen that overlays the outside scene and supports the following operations: low visibility takeoff, LVTO, using HGS guidance, Cat 1, Cat 2, Cat 3 approaches, manual visual approach, onboard navigations, displays situational awareness information, including TCAS advisory, wind shear state guidance, unusual attitude, and tail strike advisories. The HGS is composed of three components: HGS computer, overhead unit, or OHU, and combiner. For dual installation, the two identical HGS computers operate independently, providing identical symbology views to both pilots. The two overhead units and combiners operate independent of each other, one for the left side and one for the right side. The HGS computers receive input signals from aircraft's other sensors and generate a symbology set that is dependent on the selected flight operational mode. This symbology data is transmitted to the overhead unit in the form of digital signals. The overhead unit generates flight symbology from a liquid crystal display, LCD, inside the overhead unit. Then, the relay lens of overhead unit projects the symbology onto the glass display of the combiner. Now, let us see the components of HGS in detail. HGS computer. The HGS Computer 1 and HGS Computer 2 communicate through the crosstalk bus in order to transmit their status. The HGS continuously performs built-in tests, and if any failure is detected, the information is presented in the EICAS. The power source for the left side HGS computer is the DC bus 2, and for the right side HGS computer is the DC bus 1. Overhead unit. The overhead unit receives information from the HGS computer and transforms this data into a flight symbology on a liquid crystal display, LCD. The overhead unit relay lens then projects this symbology onto the glass display of the combiner. The overhead unit controls the intensity of the projected symbology on the combiner. The DC bus 2 powers the left side overhead unit, and the DC bus 1 powers the right side overhead unit. Combiner. The reflective glass element of the combiner reflects the symbology image projected from the overhead unit. The combiner has three positions: stow, operating, and breakaway position. Stow position. This is the position of combiner when not in use. To stow the combiner glass from the operating position, first put the cloth cover over the combiner glass. With the lever pushed, hold the combiner arm by the side and rotate the combiner glass up and aft from the operating position to the stow position. When the combiner is in the stow position, the combiner stow switch automatically turns off the overhead unit power supply. Operating position. This is the position of the combiner while in use. To move the combiner glass from stow position to operating position, push the release lever and hold the combiner arm by the side. Lower the combiner glass until it latches in the detent or operating position. Remove the cloth cover from the combiner glass. The combiner stow switch automatically turns on the overhead unit power supply when the combiner glass moves into the operating position. The Combiner Alignment Detector, or CAD, detects whether the combiner is correctly aligned in the operating position or not. If not, a signal is sent to the HGS computer, which will show Align HUD message on the combiner. If this message appears, slightly push the combiner arm forward and let it move back to the detent position to remove the message. Breakaway position. This is the safety feature that allows the combiner glass to rotate towards the windshield during a sudden deceleration of the aircraft, which prevents head injury to the pilot during an aircraft high-G deceleration. To move the combiner glass from operating position to breakaway position, push the release lever and hold the combiner arm by the side. Lower the combiner glass until the combiner glass latches in the breakaway position to prevent its sudden return to the operating position. Brightness control. HGS contains a brightness control device which has two modes, manual mode and auto mode. Manual mode. The control knob is pushed in to select the manual mode. The combiner display brightness can be increased by rotating the brightness control knob clockwise and decrease the brightness by rotating counterclockwise. The intensity of the display, once set, remains at the set level. Auto mode. The control knob is pulled out to select the automatic brightness control mode. The desired display brightness contrast ratio is initially adjusted by rotating the control knob. Once set, the display intensity will automatically change according to the ambient light conditions. The ambient light sensor and related circuitry also prevent blooming of the display when the brightness mode is changed from automatic to manual. Now, let us see the different symbology displays of the combiner. The combiner displays airspeed tape indications, altitude tape indications, ADI indications, and HSI indications. The airspeed tape indications are displayed on the left side of the combiner. The various symbologies are as shown. To know the details of each symbol, move the cursor over the numbers. The altitude tape indications are displayed on the right side of the combiner. You may note that vertical speed indications are also displayed in this tape. The various symbologies are as shown. To know the details of each symbol, move the cursor over the numbers. The Attitude Director Indicator ADI indications are displayed on the middle of the combiner. The various symbologies are as shown. To know the details of each symbol, move the cursor over the numbers. The Horizontal Situation Indicator HSI indications are displayed on the bottom of the combiner. The various symbologies are as shown. To know the details of each symbol, move the cursor over the numbers. System status and warning messages are shown on PFD. The PFD data and messages for the HGS include the following: low visibility takeoff, LVTO operations. LVTO in white, shown on the PFD, indicates that LVTO is on. LVTO in green, shown on PFD, indicates that LVTO is active. In the combiner, LVTO will be blinking in the right top corner for the first 5 seconds, and then it will become steady. No LVTO in amber indicates that LVTO has lost capability, but is recoverable below 40 knots and above 80 knots. In the combiner, no LVTO will be blinking in the right top corner of the combiner display. No LVTO in red indicates that LVTO has been lost between 40 and 80 knots. In the combiner, no LVTO with box will be blinking in the right top corner of the combiner display. LVTO warning. The low visibility takeoff operations warning is shown in red LVTO warning letters on the upper left corner of the PFD. In the combiner, LVTO warning will be blinking in the middle of the combiner display. HUD A3 armed. HUD A3 in white on PFD indicates that HUD A3 guidance function is armed. In the combiner, HUD A3 will be shown at the left top corner of the combiner display. HUD A3 active. HUD A3 in green, shown on PFD, indicates that the HUD A3 function is active and HGS guidance is being displayed. In the combiner, HUD A3 is shown at the right top corner of the combiner display. No HUD A3 caution. During A3 approach operations and when aircraft is above 500 feet ASL, the annunciation No HUD A3, amber letters, shows on PFD to indicate that the HUD A3 guidance function is no longer available due to system or sensor failures or data miscompares. No HUD A3 also shows in the right top corner of the combiner display. The annunciation flashes continuously. No HUD A3. During A3 approach operations and when the aircraft is below 500 feet ASL, the annunciation No HUD A3, red letters, shows on PFD to indicate that the HUD A3 guidance function is no longer available due to system or sensor failures or data miscompares. In the combiner, approach warning flashes for the first 5 seconds, then steady when aircraft is below 500 feet ASL. When HUD A3 guidance function is no longer available due to system or sensor failures, or aircraft approach attitude or position is outside the performance envelope required for the approach and landing. Runway remaining. Runway remaining distance will be displayed on the PFD. The HGS computer calculates this distance, and the same information is shown on the combiner. HGS further indications are also enunciated on EICAS to provide system status information to the crew. For aircrafts with single HUD, the EICAS messages are as follows. HUD fail. This cyan indication indicates that HGS is not available. This lack of availability is due to the LRU failure or an electrical power failure. HUD LVTO not available. For an aircraft with LVTO capability, this cyan message indicates that HGS takeoff guidance is not available. HUD A3 not available. This cyan message indicates that the HGS approach guidance is not available. HUD A3 off. This white message indicates that the HUD A3 guidance function is turned off using the MCDU HGS page. The unusual attitude symbology, or UA, is automatically activated or deactivated based upon the attitude of the aircraft. When activated UA, display replaces the curly selected operational mode symbology. The UA symbology automatically deactivates 3 seconds after the aircraft pitch or roll attitude returns to the normal ranges. When deactivated, the previous combiner display is restored. The TCAS advisory symbol consists of boxes in brackets with angular lines extending from the corner, which defines the safe and unsafe flight zones. Whenever the flight path symbol is not within the box, that is, unsafe zone, the angular lines flash. Traffic avoidance is achieved by keeping the flight path symbol in the safe zone. The HGS combiner shows wind shear alert messages that corresponds to PFD messages. Wind shear recovery guidance generated by the flight director is displayed when the vertical mode indicates wind shear. If the recovery procedure occurs during decreasing performance conditions, the guidance cue is solid and the speed error tape is not shown. Failure flags. Failure flags are displayed for invalid sensory status. It is usually indicated as large-size boxed characters. It will flash for 10 seconds and then becomes steady. Miscompare flags. Miscompare flags are provided for the following miscompares. It is usually indicated as small-sized boxed characters, and it will flash for 5 seconds and then it will become steady. To know the details of each symbol, move the cursor over the numbers. HGS is operational when the aircraft is powered up. All functions of the HGS remain operational. MCDU is an interface between pilot and the HGS system. To select the menu page, push Menu Function key on MCDU. To access the HGS page, push the Line Select key next to HGS. HGS menu page appears with the following options: runway length, runway elevation, combiner mode, auto, declutter, full, HUD A3 control, on, off. Runway length. The value of runway length should be automatically set by the flight management system. However, if this value is incorrect or does not show on the HGS page, follow these manual settings. Use the menu keypad to enter the value, which must be positive. To correct the errors on the scratch pad line, use Clear or Delete key at the bottom of the MCDU front panel. If the runway length is less than 4,000 feet or greater than 18,000 feet and is entered on the MCDU, the runway remaining value is removed from the combiner display. When the correct value shows on the scratch pad line, push the LSK next to the data line underneath runway length. The correct value is shown in green numbers on the associated data line. Runway elevation. The value of runway elevation should also be automatically set by the flight management system. Use the menu keypad to enter the value. If the runway elevation is negative, push MCDU plus or minus button. Negative sign then shows on the scratch pad line. Then, enter the new value on the scratch pad line. To correct the errors on the scratch pad line, use Clear or Delete key at the bottom of the MCDU front panel. When the correct value shows on the scratch pad line, push the LSK next to the data line underneath runway elevation. The correct value is shown in green numbers on the associated data line. Combiner mode. On the HGS page, push the LSK next to Combiner mode until the desired selection shows in green. The selection order of the data line is Auto, Declutter, Full. Auto. The HGS automatically removes the airspeed tape, the altitude tape, and the HSI during the approach. Declutter. Manually declutters the airspeed tape, altitude tape, and the HSI during any flight phase. Full. Manually forces the full symbology display after an automatic or manual removal of the tapes and the HSI. HUD A3 control. On the HGS page, push the LSK next to HUD A3 to turn on or turn off the head-up display. Now, you can interact with MCDU HGS menu page. Explore the functions which you have learned.
The reversionary panel allows control of which display is shown on the MFD. It also enables selection of an alternate air data source and the cross-side inertial reference system. You can set the display's MFD mode selector switch to the following positions. PFD. PFD information is presented on the MFD all the time. Auto automatically presents the display information of the display that has failed on the MFD. MFD. MFD information is presented on the MFD all the time. ICUS. ICUS information is presented on the MFD all the time. In the event of an electrical emergency, the display selector knob is deactivated and the PFD will be displayed on MFD1 regardless of the knob position. With the ADS button, you can select an alternate air data source. A striped bar illuminates inside the button to indicate that it is pressed. Pushing the IRS button changes the attitude and heading source from the on-side inertial reference system to the cross-side IRS. A striped bar illuminates inside the button to indicate that it is pressed. The ICUS will be decluttered if the following conditions are met. The aircraft is flying in a clean configuration, flap and gear up, for more than 30 seconds, and none of the decluttered parameters have been exceeded. If these conditions are met, the following items are decluttered during cruise: oil pressure, oil temperature, low pressure vibration, high pressure vibration, gear position, flap position, slat position, speed brake position, and on the pitch trim scale, the green takeoff band will extinguish. Pushing the ICUS full button displays all of the decluttered items. The cursor control devices, CCD, are installed on both sides of the control pedestal panel. They allow the flight crew to quickly select the displays and position the cursor within the different selectable menus. The CCDs are primarily used on the MFD for selection of formats and functions. They also provide radio tuning on the PFD and ICAS message scrolling on the ICAS display.
The Cursor Control Device, CCD, controls in detail are 3 format locating buttons. On the pilot's CCD, the left button places the cursor on the pilot's PFD. The center button places the cursor on the pilot's MFD. The right button places the cursor on the ICAS. On the co-pilot's CCD, the left button places the cursor on the ICAS. The center button places the cursor on the co-pilot's MFD, and the right button places the cursor on the co-pilot's PFD. The tuning knobs select the value or mode in the data field enclosed by the cursor. The touchpad is used to move the cursor in a display unit. Use the pad to instantly move the cursor around the display. 2 enter-push buttons, one on either side of the palm rest, are used to access the positions and selections.
The Air Data System, ADS, provides primary air data information to primary flight displays, flight controls, and other avionics as required. The pressure sensing elements of the Air Data Computer, ADC, are mounted in the Air Data Smart Probes, ADSP, and sense total pressure, static pressure, local angle of attack, AOA, and process the total air temperature, TAT. These parameters are sent to the Air Data Application, ADA. The ADSPs are located on the nose of the airplane. ADSPs 1 and 2 are symmetrically located and are further forward and lower on the nose than the symmetrically located ADSPs 3 and 4. Total air temperature probes 1 and 2 are symmetrically located. The ADC performs air data pressure calculations, which are forwarded to the Air Data Application resident in MAU, or to the Integrated Electronic Standby System for airplane fuselage effects, and sends the information to the flight deck to be displayed as airspeed, altitude, Mach, and angle of attack. The ADA corrects the local air data values received from the Air Data System. This air data information is also sent to airplane systems that require air data input, such as stall protection, flight controls, and others. The Micro Inertial Reference Unit, IRU, uses air data to calculate wind-related parameters. During normal operation, air data readouts on the captain and first officer's PFDs are from ADS-1 and ADS-2, respectively. Upon failure of either ADS-1 or 2, only the affected side will lose the ADS readout, and a failure indication will be provided to the flight crew. The affected side will automatically revert to ADS-3. In addition, the pilot can select one of the 2 remaining ADSs for the associated PFD's air data display. For 1 or 2 ADS failures, the reversionary logic for the captain and first officer PFDs can be seen in the following table. Air data information is also displayed on the MFD upper right corner. Note that this information is only visible in flight and will be removed on ground. The Air Data Smart Probe, ADSP, combines pitot, static, angle of attack, and some air data computer functions into a dual-channel unit. It consists of an air data computer attached to a multifunction probe. The MFP utilizes a single heater element to ensure that the probe strut and head remain free of ice. The ADC monitors the probe current to detect any heater failures and actively controls the heater temperature. The ADC is physically and pneumatically connected to the MFP. The MFP is a one-piece probe that contains a total pressure port, 2 alpha pressure ports, and 2 drain holes. Each port is paired to a pressure sensor located in the ADC. 2 absolute pressure sensors measure pressure data from the total pressure port and the alpha port. A differential pressure sensor measures the difference between the pressure data from the alpha pressure ports. From the 3 measured pressures, the local total pressure, local static pressure, and local angle of attack are computed. The radar altimeter system provides accurate absolute altitude above terrain, decision height enunciation, and low-altitude awareness up to 2,500 feet above ground level. One radar altimeter system is the standard system, and a second system is optional. The radar altimeter system 1 is powered by the DC bus 1, and the system 2, if installed, is powered by the DC bus 2. In a single system installation, the same radar altitude is displayed in both PFDs as a digital readout. In a dual system installation, PFD1 displays System 1 radar altitude, and PFD2 displays System 2 radar altitude. The system interfaces with the TCAS, which uses the radar altitude information to inhibit descend resolution advisories. The system also interfaces with the MAU for data distribution and integrity checking. In addition, other interfaces are performed, such as with the EGPWS system to determine airplane sync rate variation, with the DVDR system in order to record mandatory parameters. When one or both of the radio altimeters has failed, the associated CAS message, Radio Altimeter 1 fail or Radio Altimeter 2 fail, is displayed on the ICAS display. The Integrated Electronic Standby System, IESS, permits the computation and the display of the 3 main functions, should the main instruments fail: attitude, pitch and roll, standard or barometric corrected altitude, and associated barometric pressure, indicated airspeed. In addition, the IESS provides the following secondary functions or displays: indicated Mach number, VMO, MMO, slip skid indication, vertical speed, ILS, barometric pressure in hectopascal, and altitude in meters. The IESS relies on 28-volt DC power provided by the essential DC bus 2. In case of an electrical emergency, it will continue to operate powered by the ram air turbine or by the batteries through the essential DC bus 2. The system is powered as soon as battery 1 is switched to on and battery 2 is switched to auto. Then, the IESS starts its alignment phase, which requires about 90 seconds to be completed, and can be identified on the screen by its alignment flag. Note, the airplane must not be moved during the first 90 seconds after power-up, while the IESS is undergoing alignment. Moving the airplane during this period can cause in-flight attitude indication errors that are not noticeable on ground. Attitude, using the data from the respective sensors after its conversion to digital format, the system computes and displays attitude. The cage button resets attitude to provide a fast erect function. This function is not operational during the initialization mode and must only be used in stabilized flight conditions. Altitude data is provided by processing static pressure sensed by ADS-B 3 and 4. Altitude is displayed in tape format. Pushing the Standard button sets the IESS reference barometric pressure to standard, Q and E. Barometric pressure can be adjusted, starting from the standard value, by using the rotary baro knob. Indicated airspeed data is presented in tape format and is provided by processing dynamic pressure sensed by ADS-B3. In case of abnormal operation or failure detection by the internal monitoring in one or several IESS functions, the following flags are displayed: attitude, altitude, airspeed, vertical speed, and ILS. For example, if the ILS discrete label is not received or not valid, the 2 pointers and the associated scales are removed with red cross failure displayed and ILS1 displayed in amber. If the receiver is not tuned on the ILS frequency, the 2 pointers and the associated scales are removed without the display of red cross failure. Any other indication that fails will be blanked and covered by a red cross. The clock is located on the cockpit instrument panel. It is used to display the Universal Time Coordination, UTC, elapsed time, and chronograph functions. UTC is indicated from 0 to 23 hours 59 minutes and 59 seconds. A fixed colon separates hours from minutes and operates only when the function is initialized. With the 3-position selector set to INT, the clock displays its internally computed time. When set to GPS, the clock synchronizes and displays GPS time. Note: during GPS initialization, the clock displays its internal time. When the clock is synchronizing with the GPS, when no signal is present, or when false or invalid data is received, the clock displays its internal time. It displays only 0 if the internal time is not set. Pressing the Date button displays the day, month, and year in place of the UTC, but the colon is not displayed. Leap years are taken into account. Elapsed time counting is possible from 0 to 99 hours and 59 minutes. A fixed colon separates the hours from the minutes and is seen only in the run mode. The display is blanked in the non-operative mode. In the auto mode, the elapsed time counter starts only if there is no weight on wheels. As soon as weight is on wheels, the counter stops. With weight on wheels and selected to the reset mode, the counter is zeroed and blanked. Chronometer time is displayed from 0 to 99 minutes and 59 seconds. Pushing the RST push button blanks the display. Pushing the CHR push button once enables the display and starts the chronometer from 0. Pushing it a second time stops it.
The magnetic standby compass is a single, independent unit mounted on the center windshield structure below the overhead panel. It is used as a standby heading source. The compass has no system interface, but receives power for illumination via the 28-volt DC Essential Bus 1. Illumination of the compass is controlled by the standby clock dim control on the co-pilot's lighting control panel. The standby clock dim control also controls illumination brightness for the clock.
The Embraer 170 communication system is composed of the radio communication system, the flight and interphone system, the passenger address system, and the static discharging system. The radio communication system enables the cockpit crew to talk air-to-air or air-to-ground via 2 very high-frequency radios. The system also provides digitized audio warnings to the cockpit crew. The flight interphone system enables communication among the crew and to ramp personnel. The passenger address system provides a means for the cockpit and cabin crews to make live announcements and to play pre-recorded announcements via cabin loudspeakers. Static discharging has 2 purposes. to prevent the dangerous effects of lightning discharge on the airframe, and to decrease the interference static electricity causes to radio communication. The communication system consists of several antennas on the aircraft, 2 VHF radio modules in 2 modular radio cabinets provide tuning, transmission, and reception. VHF-1 is dedicated to MRC-1, and VHF-2 is dedicated to MRC-2. The modular radio cabinets are connected via the avionics standard communication bus to the MAUs, MCDUs, display units, and other aircraft systems. Via digital audio and microphone buses, they are connected to 3 audio control panels, cockpit loudspeakers, headsets, and microphones. 2 multifunction control display units on the pedestal are the primary means for selecting and tuning the radios. The radio page, which is the main interface, allows selecting frequencies and creating different setups. The control cursor device and the primary flight display are the secondary means for selecting and tuning the radios. 3 audio control panels, 1 for each crew member and 1 for the observer, provide the microphone and audio selection for all audio communications to and from the cockpit, including aural warnings. Audio Control Panel 1 is powered from DC Essential Bus 1, and Audio Control Panel 2 from DC Essential Bus 2, while Audio Control Panel 3 is powered from DC Bus 1. The microphone selection buttons enable the pilot to speak from any radio. A light illuminates inside the button to indicate that it is pressed. Only one microphone selection button can be selected at a time. The audio selection buttons enable the pilots to listen to any radio, navigation aid, or interphone channel. A light illuminates inside the button to indicate that it is pressed. Any number of selections can be made simultaneously. The telephony buttons on the right, emergency, ramp, cabin, are set up with a hot mic which provides interphone communication on a telephony basis. A light illuminates inside the button to indicate that it is pressed. More than one telephony button can be selected at a time. The audio selection button above the display enables each crew member to listen on either the speaker, interphone, headphone, or passenger address. A light illuminates inside the button to indicate that it is pressed. More than one selection is possible. The volume control knob allows adjustment of the most recently selected audio. In case of an audio control panel failure, a backup volume knob allows pushed-out bypassing of the audio panel and volume adjustment. The auto mask mic is a pushed-in switch. Pushed out, it activates the oxygen mask microphone manually when auto mode fails. Several line-replaceable units are in the cockpit for the pilot, the co-pilot, and an observer. There are boom sets, handheld microphones, and mask mics for transmitting. For receiving, there are headphones and loudspeakers. To activate transmission via the microphones, there are push-to-talk, hot mic switches on each yoke, and one push-to-talk button on each side of the glare shield. 3 jack panels are located in the cockpit. The observer's jack panel has an integrated push-to-talk hot mic switch. Air-to-air and air-to-ground radio communication is established by the flight crew via 2 VHF COMM modules. They are located in the modular radio cabinets. 2 MCDU and 3 audio control panels provide channel selection in the MRC via the MAU. The system has an automatic transmit timeout to prevent blockage of a communication channel if a mic, boom, push-to-talk button is for any reason stuck active. All communications via the audio control panels are recorded in the cockpit voice recorder portion of the DVD-R. The MCDUs provide the primary means of tuning the radios. Via the radio button, the pilot has access to the radio page 1 of 2, and via the next or previous button to radio page 2 of 2, and vice versa. To change a frequency on the radio, the pilot has 3 possibilities. First, the pilot can write the new frequency into the scratch pad and swap it directly to the active or standby frequency on the required radio by pressing the respective line select key. Second, the pilot can press the line select key next to the standby frequency to move the cursor box over it, if it is not already there. Then the pilot changes the standby frequency by turning the lower knob to change the high portion and the upper knob for the lower portion of the frequency. To swap the new standby frequency to the active, the pilot presses the active frequency line select key with the swap symbol. The third possibility is using the memory part of the COMM detail page. To access the page, the pilot makes sure the cursor box is on the desired radio standby frequency and presses the line select key with the triangle arrow prompt. To select a memory frequency, the pilot can scroll through the frequencies by turning the knobs. To activate a memory frequency, the active frequency line select key is pressed. Up to 12 memory frequencies may be stored on the radio memory page. On the MCDU radio page, the pilot tunes the frequency and then selects the corresponding microphone and audio channel on the audio control panel. To activate the tuned radio on the audio control panel, the pilot pushes the respective microphone selection button. On the display, the radio title is shown with a number between 0 and 100 denoting the volume. By pressing the push-to-talk button, the pilot can now communicate on the selected radio through the boom set, handheld mic, or mask mic. To adjust the volume, the pilot turns the volume control knob. To deselect the actual radio, the pilot presses the respective microphone selection button again. The light in the microphone selection button will extinguish and the display reverts to the previous indication. When the pilot selects a microphone selection button while another one is active, the active radio transmission is disabled and the light in the microphone selection button extinguishes. To change the volume on the previous radio, the pilot must select the audio selection button for the respective radio before turning the volume control knob. On the display, the previous title of the respective radio is shown briefly with a number between 0 and 100 denoting the volume. To deselect the audio from the previous radio, the pilot presses the audio selection button of the respective radio twice. The audio is disabled and the light in the button extinguishes. In case of MCDU failure, the cursor control device and the PFD can be used to tune the radios. The standby frequency may be adjusted by turning the rotating knob according to the MCDU. Pressing Enter swaps the two frequencies. In case of audio bus or audio panel failure, radio function can be restored by pushing out the backup volume control knob on the associated audio control panel and adjusting the volume by rotating it. This provides microphone switching directly to the VHF COMM module and from VHF COMM audio directly to the headphones. Note: only the on-side COMM functions are available to the failed panel. When the oxygen mask mic is not working automatically, It can be switched on manually by pushing out the auto mask switch. In case a microphone push-to-talk button becomes stuck, the transmission will be inhibited after a certain time, and the audio control panel display will show a stuck mic message. Loss of communication on a bus is denoted by dashes in the radio tuning windows on the PFD and MCDU. The HF-COMM, or High Frequency Communication System, is a long-range two-way voice communication system between aircraft or between aircraft and ground stations, and operates in the HF radio band from 2.0000 to 29.9999 MHz. The digital audio panels in the cockpit connect the HF-COMM system to the radio headsets, microphones, and loudspeakers in the aircraft, while the MCDUs are used to set the radio frequency and mode. Via the radio button on the MCDU, the radio page 1 of 2 can be selected, and via the next button to radio page 2 of 2 to display the high-frequency data. On this page, it is possible to tune and activate the high-frequency frequency. Tuning can be accomplished by using the tuning knob or the numeric buttons. When the tuning knob is used, the standby frequency must first be boxed by pressing its respective line select key. If the numeric keys are used, the standby frequency must be entered in the scratch pad and the respective line select key pressed. To activate the standby frequency, press the respective active frequency. Press the respective standby frequency twice, if not boxed. Otherwise, press once to go to HF page 1 of 2. The HF detail page 1 of 2 supplies the controls to tune the HF transceiver manually and from memory, or to make a mode selection. The active high-frequency or ITU channel number and modulation mode are shown in the data field. Placing the cursor at the preset data field and pressing the line select key will copy the preset frequency to the active frequency. The transfer data field interchanges the active and preset frequencies. The monitor transmitting data field is functional if the active operational mode is either the split transmit receive frequencies mode, the ITU mode, or the emergency frequency mode. Pressing the line select key sets the receive frequency to transmit frequency. This enables listening on the transmit frequency before talking on the transmit frequency. The active receive and transmit frequencies do not change, but the monitor transmit is displayed in green font. The operating mode data field shows the active system mode. By pressing the line select key, the simplex, the split transmit receive frequencies, the emergency frequency, and ITU mode can be set. The squelch type data field shows the squelch type for the high-frequency radio. By pressing the line select key, syllabic squelch high, syllabic squelch low, signal noise squelch high, or signal level squelch can be selected. The squelch level data field shows the squelch level selection as low, medium, or high for squelch types syllabic squelch low or syllabic squelch high. The squelch level can be set by pressing the line select key. The selected squelch level is shown in green font. For squelch types low or high, the squelch level is a numeric value between 0 and 31 and can be set via the tuning knob or via the scratch pad.
The emission mode data field shows the active system modulation mode as UV, upper sideband, LV, lower sideband, AM, amplitude modulated communication, or RC, reduced carrier power single sideband. The system modulation mode can be selected via the line select key and is shown in green font. The memory selection gives access to the HF memory page. Pressing the line select key shows the page. On this page, it is possible to capture a frequency tuned in memory or store a frequency identification. To capture a frequency, press the respective memory frequency to box it, and press the line select key to activate the frequency. To store a frequency or its identification, use the alphanumeric keys and press the respective memory line select key. The frequency can also be stored by pressing the respective memory line select key and rotating the tuning knob.
By pressing the next key, the HF Detail 2 of 2 page is displayed. This page frequencies can be clarified. The clarifier fine-tunes the HF frequency. The clarifier varies from -250 to 250. The entry of the clarifier value can be done via the scratch pad or through the tuning knob. If the tuning knob is used, the clarifier value must first be boxed by pressing the line select key. For the numeric keys, enter the clarifier level value and press the line select key. Upon changing the HF frequency, the clarifier value defaults to 0. There are 3 transmission power selections: low, medium, or high. After a communication system reset, the transmission power defaults to high, which should be used during the normal operation. The HF radio can be selected on and off by pressing the line select key. The SATCOM